Hello everyone, how are you? How's everything? I hope you're doing well, you're safe and sound with your families. So, as we discussed in class today, we have already covered all these frequency selective structures, and mainly filters, and we discussed about the low pass and high pass filters. And in those lectures, we learned how to find the transfer function of each low pass and high pass filter, and also we learned how to make a circuit that can give us the low pass or high pass function. We learned how to make them with RL circuits and how to make them with RC circuits, and as you remember, one circuit, the RC circuit, can work both as low pass and high pass. It depends from where we get our output. Today I'm going to tell you briefly about the bandpass filters. Bandpass filters, as you can tell from their name, they allow a certain band of the frequencies to pass, and the rest of the frequencies they need to stop. So look at this picture. This is the ideal operation of a bandpass filter. All the frequencies between omega 1 and omega 2 will pass through this filter. Any frequency below omega 1 or above omega 2 will be stopped. So this is the main difference between this filter and the low pass and high pass. In a way, you can tell that this filter is a combination of one low pass and one high pass. One low pass that basically passes the frequencies below omega 2, and one high pass that passes the frequencies above omega 1. When we put these two together, the superposition of these two low pass and high pass filters will give you a band pass filter. So I would invite you to go over lecture 11 that is posted on Moodle and read about it, but I will tell you the important things. Of course, number one, since this filter passes a certain band, between omega 1 and omega 2 there is going to be an area. This area is going to be called the bandwidth of the filter. So the area between omega 1 and omega 2 is called the bandwidth. And the frequency in the middle of omega 1 and omega 2, right here, this frequency is called center frequency, as we have mentioned here. And we usually write this frequency as omega m. So we can try to point it here, but we call this part, let's insert this omega m. So and we will place it here. This is the point between omega 1 and omega 2. So if we can figure out the central frequency and the bandwidth of the filter, we can define this filter. One thing that you need to know is that to achieve an bandpass filter, we need to have an RLC circuit, unlike low pass and high pass that we could make them only with RL or with RC. Here we're going to need an RLC circuit. So this is point number one that you need to keep in mind. Either the series combination of a resistor, an inductor, and a capacitor, or the parallel combination of the resistor, inductor, and capacitor, they can give you a bandpass filter. So point number one. Point number two that I want you to keep in mind is that, look, no bandpass filter is ideal. Look, as you remember the ideal shape, like this The rectangle can be the ideal shape that we have in mind, but we will never have an ideal performance from a filter. You will have a performance like this, in which the magnitudes below 70% of the maximum magnitude is going to be considered the fail, so they're not passing. The ones above the 70% is going to be considered the pass. So whatever is between these two light omega C1 and omega C2, between these two cutoff frequencies, are having a magnitude over 1 over square root of 2. 1 over square root of 2 is almost 0.7, the same 70% that we talked about. So this is the cutoff frequency that we're talking about. So this is the way that we're going to find omega C1 and omega C2. But if you think about it, if you just find the omega naught, which is the central frequency, and the bandwidth, usually we consider the filters to be symmetric, because this one is an extreme case, which most of the time is not happening. Most of the time we're going to have a symmetric structure that the distance between omega naught to omega C1 and omega C2 is equal. So if you just find the central frequency, you can guess the omega C1 and omega C2. Why? Because omega C2 will be omega naught plus half of the bandwidth. Omega C1 will be omega naught minus half of the bandwidth. As simple as that. So here, in order to find the value of the bandwidth correlated with the circuit components that we have used to create this filter, we have to, of course, find the transfer function, which is the ratio of the output over the input, V out over V in. Simply, as you can tell here, you can find this transfer function using a simple voltage divider. So V in times R over R plus 1 over SC plus SL is going to give you the value of V out. So that's why V out over V in is going to be this value. When you simplify it, it's going to be R over L times S over S squared plus R over LS plus 1 over LC. Again, this I don't expect you to know how to drive it. Look, it's actually great to know, but I'm not going to ask you this in the exam to drive these equations. All we are trying to do is to make sure that at cutoff frequencies, the 70% of the passage is going to be respected. So after putting them together, we're going to find out that in order to fulfill this requirement, your omega naught will be the square root of 1 over LC. This is your center frequency, okay? It's going to be 1 in an RLC circuit. Your omega naught is going to be a square root of 1 over LC. And your bandwidth, again, like forget about all these things. All what you need to know is this one. The bandwidth is R over L. This is for the series RLC circuit. For the parallel, this value is going to be 1 over RC, just for your information. So this is how we calculate the bandwidth here and the center frequency of a bandpass filter. As simple as that. Then there is another parameter called the quality factor. This is nothing new. It's nothing new. Just after you found the bandwidth and the center frequency, quality factor is the ratio of center frequency over the bandwidth. As simple as that. Omega naught over beta. So don't worry about this one. What is important is the bandwidth, which is R over L in the series RLC circuit, and the center frequency, which is square root of 1 over LC. These are the two main things that you need to know. Quality factor is just this one over that one. As simple as that. And in general, when you replace these values into the transfer function expression of the function, you will see that the general format of the transfer function of a bandpass filter is simply this one. H of S is beta S over S square plus beta S plus omega naught square, in which beta was the bandwidth and omega naught was the central frequency. So, and here is the shape. There are other combinations of R, L, and C, as I said, like the parallel combination, the series and parallel combination. They will all give you the bandpass performance, but the most popular ones would be series RLC and parallel RLC. I hope that you got the important points about the bandpass filters. Please take a look at the lecture note 11 and bring your questions to me on Thursday. Good luck, have fun, see you.